Hello and welcome to our lecture on bias variance dichotomy. This is a conceptual lecture. So you must be right now going through lectures where you're learning many of the machine learning tools and techniques, and this is not one of them. So we're not teaching you a new technique in this lecture, but we're introducing a very important concept that's prevalent in machine learning, and therefore it applies to all the techniques, I would say, that you're learning. And I would go insofar as saying this is probably one of the most important concepts that you should understand in machine learning. Okay, so let's dive into what the core concept is. The concept can be said in very simple sentence. The idea here is that while adding complexity to a model, while if you were to keep adding complexity to a model, you might improve the fit of the model, right? So you might find out that you're better describing the data, but that need not improve the predictive accuracy of this model when you compare it to new data that you get. Okay, and this concept is true for whatever type of model that you look at. So you can take an example in linear regression, and you can add complexity to it by either adding more input variables, or even with one input variable, you can add more complex transformations. So for instance, one way of just adding complexity to a simple problem where you have one input variable, one output variable, is by saying, I'm not only interested in looking at it through the standard input variable, but I would like to look at it as a polynomial. So what is the model when you have x? X is the input variable, but you can also take x square, x cube, and so on. So you can have a more complicated fit between y and x. Because in simple regression, we've always seen y is equal to mx plus c. But what if you had y is equal to m1x plus m2x square plus c? So you can add complexity that way. You can add complexity by adding more variables. Now, this is again not confined to the regression framework. Almost any method that you take, you will typically find that there's some way of getting more and more complex. So for instance, you might have already covered trees, right? Classification and regression trees. You can add more complexity by creating more and more and more branches, to the point where you have such a complicated tree, you have such a large tree where each terminal node or leaf is a single data point that you're using in your training set. So you're really there's more complexity. With k nearest neighbors, the choice of k could be a sign of complexity. With neural networks, something that you would learn in the future, the number of layers in the neural network can mean complexity. And this idea of complexity will become more clear as we talk through some examples. But the idea is that you can make the model more and more and more complex. The model that you're going to use to create this relationship between the input and output variables and the output variable, that can become more and more and more complex. And the more and more complex it becomes, you will do a better job of fitting the data that you have. But does that mean you're creating a better model? And the answer is it might not, right? Because while you might fit the data better that you have, tomorrow when you need to predict using this model, you might not do a better job of predicting, right? And we're going to see how that can happen, that can possibly happen. Now, this core concept in machine learning is also sometimes referred to as Occam's razor. That's more of a mathematical concept, and it's definitely used prevalently in machine learning. The idea there is not verbatim what I just described. The idea there is quite simple, which is that if there are two models with equal predictive accuracy, then you prefer the model that is simpler, that is less complex. So that's not verbatim, but you see how these are two highly related concepts. With the concept of bias variance dichotomy, you're essentially questioning, saying that, oh, I can add more complexity to the model and it will look like it's doing a better job of fitting the data, but am I getting better predictive accuracy? Okay, so let's actually understand this through an example. in this particular model, in the two tables that I've shown you, here is model 1, which is your good old linear regression that you know, and here is the data set. Okay, so I've used the same data set, which is the same x on the right hand side and the same y, right? But I say that I don't necessarily believe that this is the right model, that is, model 1 is the right model. What if the relationship between x and y were more complex? So I add an x square term, and x square is nothing but, it's really simple, right? It's just I take x and I square it, and I create a new column. And like that I keep on adding columns till x to the power 9, right? And finally I have all of these as potential input variables as described by this model. So y is some function of all of these parameters, and I do a multiple regression on that. Okay, so how does this work out? Okay, so here is an illustration. Here is my linear model. Okay, here are the data points that you saw before and they plotted, and here is the line that you see is the fitted line that goes through this data. Okay, seems fairly standard, so this is what you get. How does the polynomial, the one that I created before, is actually a 9th order polynomial, right? So how does that work? Well, it turns out that it does a really good job of fitting all the data points. As you can see, this 9th order polynomial described by this black curve goes through every single data point, and that should not be surprising. You have 10 data points and you're using a 9th order polynomial to fit it. There is enough flexibility in the model, in the coefficients, there's enough complexity in the model where you can actually go through each data point. Here in the first model, it's a straight line, right? Even if it wanted to, it cannot. Even if I had, and I am using the flexibility to put this line wherever I want, right? I can move this line up and down. I can rotate this line, but the best job that I can wind up doing is actually the line that you see on the screen. So I did a simple linear regression, which does try to fit as many data points as possible, and this is as best as it could do. Now with a 9th order polynomial, when it tries to do that, it does a really good job. It fits all the data points. So you're sitting there going like, wow, so maybe my system is a 9th order polynomial, but it's not. I'll let you in on a secret. This actual data between x and y was created by actually a linear system with some amount of noise, right? So your true equation, the true relationship, which, because I'm the god out here, I'm the one who's actually creating these data points. So I have this oracle. I'm letting you in on the secret that I actually created these data points through some y is equal to beta naught b naught plus b1 x, and not x squared and x cubed, but there was some error, some noise, right? Like any regular system. So given this, it looks like the 9th order polynomial still did a better job of fitting, right? The fit is great. But let's look at how these two models compare when they have to predict another occurrence, right? Here is the fitted model, the same graph as above in the linear model, but I create a new data set, right? I create a new data set and I see how well my line does as a job of predicting what's going to happen next. And the answer is, it doesn't do too bad, right? So this is the predicted line. The blue line is the predicted line that I got from my training data. Now when I go get new data, it looks like I missed target a couple of times, and I probably should expect that given what I know right now, that there is some amount of noise in the system that is irreducible. But what this basically means is that tomorrow when you come to me with saying that, hey, 4.5, what do you predict? I say, I'm going to predict this value, and in reality I wind up seeing this value. Okay, the line in red is what I wind up seeing in the field when I make a prediction. And the prediction I make is where I wind up, what I wind up using as the blue line. Okay. Now, what do you see in terms of predicting with the ninth order polynomial? You actually do quite terribly bad. I mean, look at this data point, right? So this data point where it's 1.5, my prediction at 1.5 would be something close to minus 40, minus 39 or whatever, right? So at 1.5, if I were to use this ninth order polynomial as my fitted model, I would be predicting minus 40. But look at what I actually got, right? I got plus 15. So I was almost off by, like 55 units, whereas I'm never off by that much with the linear model. And you're going to see the same kind of weird practice here. In fact, while at something like 0.5, this model just goes through the roof. I can't even fit it inside the graph. So clearly the ninth order polynomial, while it's doing a great job of fitting, does a very bad job of predicting, right? And if my goal, more often than not, I should say bad predictor. Okay, my goal more often than not is to really come up with good predictive accuracy. So with most machine learning problems, you're just not trying to fit a model to the data. That doesn't buy you too much, but you want to create a model that can be generalized, to other situations. So tomorrow when you get a data set, because what are you going to do with the model? You're either going to predict or you're either going to interpret the model. In either case, you need to acknowledge that what you have, the data that you have, is nothing but a sample. And if you had taken another sample, if it turns out that you would have told a completely different story, then maybe the way you're doing things is not really correct. My whole point is that, for instance, if you had seen the red star data, right? In the linear regression model, you might have created a slightly different line. Maybe the line would have looked a little bit like this, right? But think about what you might have done with the complex polynomial. You might have created a completely different polynomial function that again, it will go through all the red data points. But if for one sample you create one story and for another sample you create a completely different story, then maybe the way you're doing things is not really accurate. So here is what we showed you, the system where it was truly a linear system, and clearly how using a linear model made more sense than having a more complex model. Now what happens when there is more complexity to the system? Let us, for instance, say that my true model was quadratic. Okay, and that's what I'm going to show here. I'm going to take a quadratic model and then see what happens when I try a linear fit. Okay, so here is a quadratic model. This is the truth that the machine learning algorithm does not know. That in the world, I will never know that the true system is quadratic. The only thing that I have is data. So I've shown you the data. I'm just letting you in on the secret that for today's exercise, I created this data. So this is the data, this is the model, that I created this data using this model and adding some amount of noise or uncertainty. Okay, so the model that is creating this data is actually is more of a y is equal to beta naught plus beta 1 x1 x, let's just, because there's only one x, and beta 2 x square. So I'm using some model like this with some b0, b1, b2 plus some amount of noise. Okay, obviously if you knew that this was the model, then this is the model you're going to try and fit, right? I mean, if you knew this was the model, then this is the model you should use with the truly known b1, b2. So you don't even need to do any kind of machine learning or statistics exercise. But sadly, you're only given the data and you're not told which model it is. Now let's see what happens if you had this data and then you try to fit a line, right? This is one fit. But to kind of give you a feel for what happens when you do this many times, I generated another set of data points using this model. So I've shown you only one set of blue dots, blue small mini circles, but if I created another set of blue mini circles and then fit a line, I fit another line. But one thing you should notice is, look, all these lines are in general more or less the same, they're trying to do the same job, and in general, they wind up failing chronically in certain places. They always wind up underestimating in this region because they're always under the truth. They always wind up overestimating. So each time I do this exercise, it looks like I'm chronically off in certain areas, but I'm fairly consistent. Each time I do this exercise, I wind up kind of creating the same line. Now what happens when you have a ninth order polynomial? What happens is you're still not doing too great. And the reason you're not doing too great is because this is a quadratic system and you're trying to fit something so complex, right? So you're still overshooting a lot, but there are a couple of things to notice. One, in general, as expected, as shown in the previous slide, you're not always telling the same story. One time you're telling one story, the next time you're predicting vastly different. This kind of extreme variance from one kind of prediction to the other is not seen in the linear fit. But take another look. You're not always being chronically off in certain areas. Yes, this is only 5 such fits, but imagine if you had 5,000 such fits, right? Even if you had 5,000 fits in the linear model, you will always be overestimating some regions, you will always be underestimating some regions, and that's called bias. Whereas in the ninth order polynomial, the idea is that yes, there's so much variability, but if you were to do many fits, on average you might not be off from the blue line. And that's useful in concept, it's not useful in practice, because in reality you're going to get only one data set and you're going to try one fit. So if it's off, whether it's because of whatever reason, but it really helps to understand why it's off, right? Here in the linear fit, it's off because you're chronically always going to be off because you're trying to fit a very rudimentary model, a very simplistic model for something that's a little more, in reality, more complex. The model, the reality is more complex. Okay, so this is more complex because it's a quadratic, right? And the model you're trying to fit is too simplistic because the model can only be a line. So it's a line which is, simple. Whereas, so here what you're going to witness is a lot of, some regions you're going to be always off. Whereas out here in the ninth order polynomial, there's just so much variability because you're just getting fooled by that pure noise. It's the same thing that you saw in the previous equation. Nothing is really, in the previous slide, nothing has really changed. You're still trying to fit something that's a model that's overtly complex to a system that is not that complex, right? We went from a linear data source to a quadratic data source, but that still doesn't warrant a ninth order polynomial fit. So there's a lot of variability. And this is the point that gets captured in what is really described as a bias variance dichotomy. This graph is taken from the Hastie and Tibshirani and Friedman book, Elements of Statistical Learning. And it captures what we've kind of tried to illustrate in the last 2 slides, which is as model complexity increases, it looks like you are doing a very good job of fitting the data. This is nothing but the fit. Okay, so you take the data and look, your error you want very low error. So as you keep on making a more and more complex model, you're going to go through more and more data points, right? But at some point, your ability to predict, so this is prediction on new data, right? The red line is prediction on new data. The blue line is the fit on the data that was given to you for training. So it's called the training sample, and the prediction is done on the test sample. Your prediction keeps on getting lower to a sweet spot of model complexity. And then after that, it goes up. And what is that sweet spot? That sweet spot would be attained if you were able to match the exact complexity of the system. So if you had a quadratic system, for instance, and you use a quadratic model, that might have been the sweet spot. And so if you have a complexity, that's perfect, and what we are going to do is, if you don't, in the real world, you won't know what the true model is, right? So how do you figure out what this complexity should be? And that is going to be covered in our lectures on validation, right? How do you validate a model, or how do you fine-tune some parameters of a particular model? Again, it can be k-nearest neighbors, it can be trees, it can be neural networks, it can be support vector machines, it can be a simple regression. But if there is some kind of tuning parameter there that can increase or decrease complexity, how do you go about increasing and decreasing complexity, seeing what works best, and then choosing the appropriate one? That we capture in validation, the lectures in validation. But in this lecture, we want to create an appreciation that as model complexity increases, the fit becomes better. The prediction, you need to find that sweet spot of model complexity. And that's the core idea. The other thing is also, the other idea here is that, yes, when model complexity is low, you don't do too well in terms of your prediction. But the reason for that is because there is high bias, meaning that in that linear regression, if you remember, right, you were always off. When you were trying to fit that linear regression to that quadratic function, you were always off in certain regions. So you had a high bias and low variance. What we mean by that, and I'll go back to that slide, is you were biased in certain regions. So these are regions where you have bias, right? You're always going to be off, right? Because of the nature of you trying to fit a line through a curve. But you have very low variance. The variability between many such fits is low, right? So on any given day, you get any given data set. It's not like you're going to come up with a completely new equation. So that's what we call as high bias and low variance. So high bias and low variance. Okay. Now you step over to the ninth order polynomial. Here, the bias is not that high. It's not like I can tell you that you're going to chronically be under predicting or over predicting in some regions. So this has low bias, right? So I can't tell you upfront that you're going to be always off in one direction, but it's got high variance, right? What we mean by that is, on any given day, if I take any given data set, I take a sample and I try to fit this polynomial, I don't know which line I'm going to get. I mean, this line predicts some astronomically high value out here, whereas this curve predicts some astronomically low value out here. So there's like such high variance. On a given data set, I don't know how I'm going to be predicting, and therefore, if I can have such high variance, it just means that I'm probably not going to do a very good job of predicting, right? I don't even know what I'm going to be predicting. So that's the concept between the bias variance dichotomy, which is that when you go for lower model complexity, you get high bias and low variance, and when you go for higher model complexity, you get low bias and high variance. And this is a very important concept to internalize with respect to machine learning, and it is going to be extremely important even in terms of applying more advanced techniques. So I hope the bias variance dichotomy was clear. Thank you.